Is Dr. Dhinakar, professor in the Department of EC, Bharat Institute of Higher Education Research. So now today I'm going to take a topic on transmission line concepts. It is under the subject transmission line and waveguides. It has got the course code U18Pcec502. So let us see the important things under transmission line concepts. So the transmission line is divided into small units where the circuit elements can be lumped. Assuming the resistance in the line is 0, then the remaining circuit elements being the inductor and the capacitor. As the resistance is 0, then the transmission line can be modeled as an LC ladder network with inductors in the series arms and the capacitors in the shunt arms. So it's an LC ladder network with resistance being 0 and the inductors are put up in series arms and the capacitor being put up in the shunt arms. So by determining the value of the inductance and capacitance, the velocity of the propagation of energy down the line can be found out. So once you know the values of the inductor and the capacitor, we can find out the velocity of the propagation of the energy. So time taken for a wave to travel 1 unit length is equal to T of S is equal to root of LC. That is otherwise given as LC to the power 0.5. So velocity of the wave is given in meter per second and it is given as V is equal to 1 by T, where T is already given as T is equal to root of LC. And now, what is the impedance at any point? The impedance at any point is equal to Z. Z is equal to V by I, where you know V is the voltage and I is the current. So Z is also given by the equation Z is equal to root of LC. So now let us see some of the important properties of the transmission line. So it has got 2 conductors running parallel, can propagate a signal at any frequency. At high frequency, it becomes very lousy. Can handle low or moderate amounts of power. It can handle low or moderate amounts of power. Whereas sometimes it may not be best suitable for high amounts of power. Does not have signal distortion. If at all there is loss, there will be some sort of distortion. It does not have signal distortion and may or may not be immune to interference. Does not have EZ or HZ components of the fields. You all know what is EZ. EZ electric field intensity, whereas HZ magnetic field intensities. So these components may not be present in this transmission lines. And now the figures for the coaxial cable has been shown, and as well as a twin lead diagram also has been shown in the figure. And now a Cat5 cable drawing, an image of a Cat5 cable has been shown in the PPT. And another important thing that has been shown here is the 2 wires of the transmission line are twisted. They are twisted in order to reduce interference and radiation from discontinuities. They have been twisted to reduce the interference and the radiation from discontinuities. So that's why it has been that the 2 wires has got twisted. Now, transmission lines are more commonly met out on the printed circuit boards. Now, some of the examples that has been shown here are microstrip. It can be met out on the printed circuit board, and you could see the diagram of the microstrip here, where you see here that epsilon R refers to the relative permittivity of the medium, and we have got W and H, where W refers to the width of the strip. And H refers to the height. There you can see the diagram of the microstrip. And the next one is a strip line. There also you can see the image of a strip line where you have got W and H. Here W seems to be somewhat smaller when compared to H. And again here we have got epsilon R, it's opposed to relative permittivity. The image of the strip line has been shown very clearly, and you can easily find out the relationship between H and W. And the image for the coplanar strips also been shown there. And you could see that as the name suggests, coplanar strips. They have got two strips of equal width W, and they have got a height h. And the image has been clearly indicative of the coplanar strips. And the last one is coplanar waveguides. Here also we have got a W and H specified in the diagram. And here you could see that three strips where the middle of the strips being a smaller one, whereas on the two sides of the middle smaller chip you have got strips of equal width, whereas we got the height H also being mentioned here, and the image has been very clearly indicative of the coplanar waveguides. And now, as transmission lines are more commonly met out on the printed circuit boards, here is an example for a microwave integrated circuit where a microstrip line has been used as the transmission line. It has been clearly and very legibly marked on the printed circuit board. This microstrip line has been used as the transmission line, and you could see the diagrams very well. And most of the transmission line can be met out on the printed circuit boards. And next, coming to the fiber optic guide, which is more recently used as, which is more prominently and more frequently used as the transmission line. So it has got so much of important properties, and let's see these properties. It uses a dielectric rod. A fiber optic guide uses a dielectric rod. Can propagate a signal at any frequency. It can propagate a signal at any frequency. Can be made to have very low loss. Has minimal signal distortion. Very immune to interference. Not suitable for high power. Has both EZ and HZ components of the fields. So it has got all the positive points. So that's why it's widely used as widely used for transmission line. So now you could see the images for fiber optic guides. And the first one, you could see the various fiber optic guides in various colors, and you could see the diagrams clearly mentioning all the things. So fiber optic guide is more widely used for transmission lines in the recent times, and it has got almost all the positive points to make the transmission line very effective and good. So next, what are the two types of fiber optic guides? The first one is the single mode fiber. The main point about the single mode fiber is that it requires the fiber diameter to be smaller relative to the wavelength. As compared to the wavelength, the fiber diameter should be very less. That's the main point about single mode fiber. And the other point being that carries a single mode as with the mode on a transmission line or a waveguide. The next comes the multi-mode fiber. Here, the most important point is that has a fiber diameter that is very large relative to a wavelength. It is just quite opposite to that of a single mode fiber, where the fiber diameter is small compared to the wavelength, whereas here in multi-mode fiber, the diameter is very large compared to the wavelength. It operates on the principle of total internal reflection. So next one. As you all know very well that telegraphic equation. So as you want to combine this, you have to take the derivative of the first one with respect to Z. Taking the telegraphic equation, you know very well that dou V by dou Z is equal to minus Ri minus L dou I by dou T. So that one being the telegraphic equation, we are making derivative of that one, we are differentiating that one. Then we have dou square V by dou Z square is equal to minus R into dou I by dou Z minus L into dou by dou Z into dou I by dou T. So this can be further simplified by making substitutions, proper substitutions, and then the simplified equation being that dou squared V by dou Z squared is equal to minus R into minus GV minus C into dou V by dou T, the bracket gets closed, and minus L into minus G into dou V by dou T minus C dou squared by V dou T squared, the bracket gets closed. So So this giving the equation of the transmission line, and this this is finally has been written in a simplified way, and that we could see that dou squared V by dou Z squared is equal to minus R into minus GV minus C into dou V by dou T. The bracket gets closed, minus L into the bracket opens, minus G into dou V by dou T minus C into dou squared V by dou T squared, the bracket gets closed. Hence, we can write that as we do have LHS and RHS in the previous equation, that moving the RHS onto the left-hand side, we get the equation as just like this. Dou squared V by dou Z squared minus RG into V minus the bracket opens RC plus LG, the bracket closes, into dou V by dou T minus LC into dou squared V by dou T squared is equal to 0. So this is after making the equation equated to 0. This equation looks more or like second order differential equation. The same sort of equation holds good for I also. As you written the equation for V, the same sort of equation may hold good for I also, for current also. As this is a second order, as it looks like a second order differential equation, they can go on to find out the solution for this one. So this being quite the equation for a transmission line. And for time harmonic waves, dou squared V by dou I squared minus RG into V minus RC plus LG into dou V by dou T minus LC into dou squared V by dou T squared is equal to 0. This being the equation for the time harmonic waves. And in the after simplification, we can go on to write that T squared V by D Z squared minus RG into V minus RC plus LG into J omega V minus LC into minus omega squared into V is equal to 0. This is after simplification, we can put it on like this. And now we can further go on to say that D squared V by D Z squared is equal to RG into V plus J omega into RC plus LG into V minus omega squared LC into V. So note that RG plus J omega into RC plus LG minus omega square LC is equal to R plus J omega L into G plus J omega C. So we all know very well that the impedance Z is given by R plus J omega L in the complex form, whereas the admittance Y is given in the complex form as G plus J omega C. Multiplying on this impedance into admittance, we get this one R plus J omega L into G plus J omega C, which is equal to the left hand side of the equation as Rg plus J omega into Rc plus Lg minus omega square Lc. So then this one can be simplified by making these substitutions. We can simply write that d squared V by dz squared is equal to Zy into V. So this is after making the substitution, we can write. So now the equation of the transmission line getting modified to gamma squared is equal to Zy. Then we can say that d squared V by dz squared is equal to gamma squared into V. So as this being a second order differential equation, we can have the solution for this one, and it is given as V of Z is equal to A into e power minus gamma Z plus P into e power plus gamma Z, where gamma is the propagation constant, where beta is the phase constant, where alpha is the attenuation constant. For all the things about the constants, alpha, beta, and gamma being the constants for various things. And now conventionally we can write it as gamma is equal to R plus J omega L into G plus J omega C to the whole power 1 by 2. That is gamma is equal to root of bracket opens R plus J omega L bracket closes, and then bracket opens G plus J omega C and the bracket closes. That is gamma is equal to root of this one. Then we can further say that root of Z is equal to root of modulus of Z into e power j theta by 2. So as I already said that gamma can be written in the complex form as alpha plus j beta, where gamma is nothing but the propagation constant and alpha being the attenuation constant and beta being the phase constant. That is, propagation constant has been written in terms of the complex number as attenuation constant plus imaginary part of the phase constant. So that's the thing here. And now a forward traveling wave. A wave traveling in the positive direction of the z-axis can be called as a forward traveling wave. You could see the diagram, you could see the graph very well there. The wave that has been shown in the graph has been traveling in the forward direction of Z. Therefore, it can be rightly called as a forward traveling wave. And you could see that for the first wave, you see that lambda g being the wavelength, and the first crest. What is the velocity at the first crest? And that one, the velocity, the the voltage has been described as V of Z is equal to V naught plus into e power minus gamma Z. That is equal to V naught plus into e power minus alpha Z into e power minus j beta Z. That is V plus in terms V plus of Z of t is equal to real part of V naught plus into e power minus alpha Z into e power minus j beta Z into e power j omega t. That is equal to modulus of V naught plus into e power minus alpha Z into cos omega t minus beta Z plus pi. So here we get to have one more important thing, that beta is equal to 2 pi by lambda g. As you all know that lambda being the wavelength and beta being the phase angle. So the relationship between the wavelength and the phase angle is being given as beta is equal to 2 pi by lambda g. And you could see the diagram for the wave traveling in the positive direction. Just coming to the phase velocity. So tracking the velocity of a fixed point on the wave. So we have to identify a fixed point on the wave. As you could see in the diagram of the wave, here we have taken the fixed point as the crest point, where the velocity is taken as v of p, which is nothing but phase velocity. The velocity at the crest of the waveform is supposed to be the phase velocity, and it's given by the formula v of plus in terms of z of t is equal to modulus of v naught into e power minus alpha z into cos omega t minus beta z plus pi. So this being the phase velocity, the forward traveling wave is given by this equation. And now, in further into the phase velocity, we can make some substitutions. That is omega t minus beta z is equal to constant. So if that is the case, omega minus beta into dz by dt by taking t as common for both the terms. Therefore, we get the equation as omega minus beta into dz by dt is equal to 0. Further simplifying this one, we get dz by dt is equal to omega by beta. Therefore, this can be written as Vp, that is a phase velocity, is equal to omega by beta. That is Vp is equal to omega by beta. That is simply phase velocity is equal to omega by beta. So in expanded form, we can write Vp is equal to, that is phase velocity is equal to omega divided by, where beta can be written as imaginary part of r plus j omega L into g plus j omega c to the power 1 by 2. That is imaginary part of root of r plus j omega L into g plus j omega c. So that is how the phase velocity has been described here. And now let's move on to the characteristic impedance. So the characteristic impedance is given by the notation Z0, where now you could see in the diagram that we have got a signal where both voltage and the current has been represented as V of Z and I of Z. This waveform, this particular wave has been traveling in the positive direction of Z axis. Therefore, it can be termed as a forward traveling wave. As you know that impedance is normally given by the formula Z is equal to V by I. Therefore, here also the characteristic impedance Z0 is given by V of Z divided by I of Z. So V of Z can be further given by V0 plus into e power minus gamma Z, where I of Z is equal to I0 plus e power minus gamma Z. So now in the place of Vz and Iz, we can substitute these equations. Therefore, Z0 becomes, Z0 is equal to V0 into e power minus gamma Z divided by I0 into e power minus gamma Z. So cancelling out e power minus gamma Z, we will be getting Z0 is equal to V0 plus divided by I0 plus. So therefore here Z0 is just a mere number, not a function of Z. So the characteristic impedance Z0 is given by the formula V0 divided by I0, and it's a mere number and it's not a. So now coming back to the telegraphus equation, you all know, we know very well the telegraphus equation is dou V by dou Z is equal to minus Ri into minus L into dou I by dou T. So this can be written as dV by dEz is equal to minus Ri minus j omega Li, that is equal to minus Z into I. That is dV by dEz is equal to minus Z into I. So now multiplying the whole thing by e power minus gamma Z, we are having that minus gamma into V0 into e power minus gamma Z is equal to minus Z into I0 into e power minus gamma Z. So now we are getting this one, a characteristic impedance. And now from this we have this Z0 is equal to V0 by I0. That's what we have got it already. That is further can be written as Z0 is equal to Z by gamma, that is equal to Z by Y to the power 1 by 2. That is Z0 is equal to root of Z divided by Y. That is Z0 is equal to characteristic impedance Z0 is equal to root of impedance divided by admittance. So now using this complex form, Z is given by R plus J omega L, where admittance Y is equal to G plus J omega C. So now using this particular terms into the formula, that is Z0 is equal to Z by Y to the power 1 by 2. Substituting this complex numbers onto that one, we have Z0 is equal to R plus J omega L divided by G plus J omega C to the power 1 by 2. So now you have waves in the both directions. That is waves traveling in the positive direction of Z as well as wave traveling in the negative direction of the Z. For that, we have V of Z is equal to V0 plus into e power plus gamma Z plus V0 minus into e power plus gamma Z. This can be further written as V of Z is equal to modulus of V0 plus into e power j pi plus into e power plus alpha Z into e power minus j beta Z plus modulus of V0 minus into e power j pi minus into e power plus alpha Z into e power plus j beta Z. So now you see that this one is for waves traveling in both the direction. There is wave traveling in the forward direction of Z axis as well as wave traveling in the negative direction of the Z axis. So now you see that this can be further simplified and can be written as V of Zt is equal to the real part of V of Z into e power j omega t. That is equal to modulus of V0 plus into e power minus alpha Z into cos omega t minus beta Z plus pi plus modulus of V0 minus into e power plus alpha Z into cos omega t plus beta Z plus pi minus. So this one is a equation for both the waves, that is both in the forward direction as well as in the reverse direction. And now so coming to the end of things, there is so far we have discussed about transmission line and the important concepts. There is how you can form a LC ladder network, and whenever the resistance becomes zero, how does the transmission line looks like? It becomes a LC ladder network where you see that always inductors being connected in series and the capacitors being put up in the shunt arms. So that is one of the thing. And then the next thing what we saw about is that what are the two modes of operation? There is the most widely used transmission line in being the fiber optic guides, where we have got two modes, single mode and the multi-mode fiber. The important thing about that is that the fiber diameter being very less when compared to the wavelength in case of single mode, whereas in the multi-mode, the case is rather opposite, where you see that the fiber diameter being more than that of the wavelength. So combining those two things, we want to make an equation for the transmission line, and the basic equation being the telegraphic equation. where you see that always that you have to remember dou v by dou z is equal to minus ri minus l dou I by dou t. So this being the telegraphic equation upon which we make the differentiation, and you are getting the equations. And of course, we are we are about to find out the characteristic impedance is it not. That is very much important for a wave to travel to minimize the losses and to travel with very less losses. So further we find out is it not is equal to V naught by I naught, V naught by I naught. And now we made a complex substitution for Z also. We made a substitution that R plus J omega L, and for omega also for Y, for admittance Y, we made a substitution G plus J omega C and out. So upon all the substitutions, we get among all the substitutions, we get to find out that we get a simpler formula, and these are all some of the important concepts in transmission line. And before concluding that, before concluding that, I want to say a few more points about that. As these derivations, the transmission line derivation and the equation for the harmonic is so important that from examination point of view, and this